What's up, people? This is Milos. Welcome back to my channel as I take you on another exciting data visualization journey with R. This time, we're going to be playing with the noise data from the European Environment Agency and create some very crisp noise traffic maps of specific regions. We're going to start off by installing and then loading the libraries that we need. And the first library that we need is ArcGIS, which is going to help us connect to the ArcGIS API and get the noise data that we need. Now, we used it in one of the previous tutorials, so you can also check it out there, how we installed it and unloaded it. But for now, what we need to do is, first of all, install one of the packages, which is called Remotes. And Remotes is going to help us install ArcGIS from the GitHub development version. Meanwhile, this package was also published on CRAN, but I like to install it from the development version because I can get the freshest version of this package. So once I install the remotes package, I can go ahead and call here install GitHub option. And over here, then I'm going to specify the name of the repo. So that's r-arcgis and then /arcgis. And then you also want to install any possible dependencies, so you need to also include this dependencies attribute equals true. Now we need to just load. So the first thing we need to do here is check if the Pacman package is installed. If it's not installed, you can simply install it by using just install packages and then also here Pacman. All right. And once this is done, what you need to do is simply load the packages. What Pacman is going to do, it's also going to install the packages unless you have them, but they need to be available, of course, on the CRAN. All right, so the function is p_loads, and then here you provide the list of libraries that you need. The first one that we will need is geodata for fetching the regional boundaries in this data set. And the second one is, of course, ArcGIS, which we already installed, so we can just use Pacman here to load it. The second one is the umbrella package Tidyverse. From this one, we'll be using the dplyr for data wrangling and also ggplot2 for data visualization. Then we'll be also working here with OSM roads, which we will turn into SF format. So we definitely need the SF package to work here. And then, of course, the noise data is going to be in the raster format. So we'll be using Terra as always to not just load, also modify these raster files. Then I would also like to add street view, and map tiles package is perfect for that purpose. And then finally, to also visualize within ggplot2 to visualize raster files, we can use here tidy Terra package. The next thing is to get the regional boundaries, and for this purpose we'll be using the geodata to first of all get all the regional boundaries for a selected country. In this case, for Belgium, we'll be getting the Brussels region. And let's actually first of all get the country boundaries together with the subnational regional boundaries. So within geodata, there is a function which is called GADM. This actually will fetch global administrative boundaries. So what you need to do here is first of all specify country for which you need to fetch the boundaries. So that would be Belgium, and you need to provide ISO 3 code. The second one is what is the subnational level that you want to do. So if you choose here level 0, basically it's going to return you just national boundaries of Belgium. But in this case, it's going to return the next administrative level division, so the regional level. And then finally here, you need to specify the pathway where you want to save, because this is going to be locally saved. Now, this is not going to be in the SF format, but we want it to be in the SF format so that we can work with it in R. So what we will do in the end is simply coerce this into an SF format using this function here. So once we get these national boundaries, we can then get the regional boundaries. So you can actually inspect this file here to see what are the field columns, and one of the field columns is called name_1. So this is the name of the region, and for the Brussels we can also then filter this one. So then we go and create a new object region SF, and then we use actually this one here. We subset the country boundaries with the regions, of course. So that's country SF, and then over here we specify that name1 needs to be called Brussels. All right. And then once you actually do that, you can also go ahead and plot if you want this using just simple the base rplot function. But for us, what is more important here is to create the bounding box here, which we will use several times throughout this tutorial to fetch, first of all, the OpenStreetMap roads, but also then to fetch, for example, the street views. So to create the bounding box here, we simply use stbbox function and then just pass here region SF. In today's tutorial, we'll be mapping traffic noise, and for that purpose, we'll be using the noise data from the European Environment Agency, which is available on this website that I will also share with you in the description box below. Now, in terms of the data sets, there are several ones that are included here, and the one that we need is the rasterized noise contours data. Now, over here down, you can see the data sets, and here is the actual latest version. Now, the reason why we are taking the raster one here at 10 meters is because we want to calculate what is the specific noise level for every major road. So if you go down here, you will notice that the actual data is not really available through a direct download unless you are actually registered for this service, but it's available on the S3 website, and that's why we're using ArcGIS layers package to communicate with it. You will also notice that apart from specific types, such as, for example, airports, industry, railways, and major roads, there is also something which is called LDEN and LNight. Well, LDEN means both day, evening, and night, and LNight is only for night. So we want actually day, evening, and night because it shows a more comprehensive picture. And we're also interested in major roads, so I'm going to scroll down here. And there is this link which is already highlighted, we will click actually on this one, and this is going to open a new window, which is going to lead us to the interface of this ArcGIS REST API. And this is where we are actually going to work with it. Now, the next thing that you want to do is actually copy this link here, and we will then paste it back in R in order to build a query that will get us the data. If you want, you can also explore a bit here. It gives you information about the extent, about variables, different variables, about the authors, about the fields in this data set, and other things. But for now, what we will do next, again, just simply copy the link to this one, and then we will go back to R where we will fetch the data we need. All right, guys, if you followed all the steps, you copied that URL and pasted it here. It should be here in your editor. So what I'm going to do next is simply put double quotation marks around this one and effectively coerce it or convert it into a string. And then I'm going to pass this to a URL. So this is my URL object. The next thing that we want to do is finally use ArcGIS layers to, of course, open the connection to this source, and then, of course, load the data in the raster format. So I'm going to, first of all, call this noise data, and then I'm going to use here ArcGIS layers, and then here arc_open. So this is going to open the connection to the data, and I'll just pass here this URL. And once we do that, we can then coerce this into a raster format. So I'm going to call this noise_raster. And again, I can call here ArcGIS layers. And then from ArcGIS layers, this time we'll be using this arc raster, right? So here, what we need to provide here is the connection name. So it's noise data. And then there are several convenient things here. So you don't need to load all the data. You can just load the data for your extent. And luckily for us, we created our extent when we created this bounding box of our region. So we can simply pass those 4 elements of the bounding box. So that would be xmin. And then over here, what you want to do is you want to get from this region bounding box the column name under the same name, so also xmin. So this is the minimum longitude value, and then you need to repeat this for all the 3 remaining ones. So the next one would be then the maximum longitude value. Of course, always remember to also change here the names. And then once you do that for the longitude, you should also do it for the latitude. So simply replacing here x with, or actually replacing x with y, exactly. And once you have that, it's not over, because you also need to provide the coordinates reference system that you will be using this CRS attribute here. So what we want is we want the same one that is already used in that and that region SF object that we previously downloaded. So we can just pass here that we want the same coordinates reference system that a region SF object is using. And then optionally here, you can also specify the width and the height in pixels. I'm just going to go for a very high resolution here. So 4000 by 4000. But this might actually not change that much. So you can basically, you don't need to follow this one. And then once you actually run this, you also want to check what are the unique values. So what are the unique values of this raster file? So what you can do here is simply use Terra values and then pass this noise raster and then actually run this whole thing. And then we can check what are the values that it has. So this dataset offers actually 7 possible values. So that's from 0 to 5 and then also 15 for NA values. Over here, we only have 1, 2, 3, 4, 5, and then also 15 for missing values. So what we essentially want to do is we want this 15 to convert simply to missing values and then just like omit throughout our tutorial. So the first thing that we will then do here is replace, of course, the values. So I'm going to create a new object, which is going to be the clean object, so to say, because we will be using here some transformations. So for that purpose, I will from Terra call this if-else function or if-else. And then I'm going to write here, so if noise raster equals 0. I know 0 is not in our data, but imagine if it is for some other extent, you definitely want to have this. So first of all, if it equals 0, or, so this actually vertical here sign means or, if noise raster equals 15, then we convert it to NA, otherwise we simply return this noise raster here. Our roads noise data relates actually to the major roads. So that means that if we want to actually calculate what is the value of the noise for certain major road routes, we definitely need to get the vectors for the major roads. And this is why from OpenStreetMaps we'll be doing that. What I actually have here in front of you are the names of major road tags that exist in the OpenStreetMap. So those are the motorway, trunk, primary, secondary, and tertiary, and also all their links. So I wrote it here so that you actually don't need to write it again. What we will do here is simply create a list, of course, of these tags, and I'm going to call them simply major roads here. And to create a list in R is very easy. You just need to put brackets around this and also use the C to indicate that this is a list. All right, and then once you actually do this, the next thing is to load the OSM data. Now, I didn't actually include at the beginning the OSM data package, but I will definitely do it after the tutorial. Now, what we need here is to create a new object, which is OSM roads, and then use the OSM data package. OSM data package, what it does is it helps us get for certain bounding box certain features. And in this case, the features that we want are major roads, which are also called highway. So the major tag is actually highway in the OpenStreetMaps terminology. So to write your query, you need this OPQ. OPQ is the function within OSM data. So here you need to specify the bounding box. So for us, that's a region bounding box. The second one that I like to also put here is the timeout in terms of the seconds. So I put, for example, to 180 seconds. If you think that this is too short, you can also increase it. And then also I like to put the memory size here because sometimes if you're fetching, for example, a lot of roads, that can be a problem. So I here choose a quite high memory size. And then once you actually write this query, the second thing is to get the data that we need. So for that purpose, you can use add OSM feature here. Then you need to specify the key. And as I said before, highway is the general tag for all the roads in this OpenStreetMap terminology. But what you also want to do is you want to filter further here and to get only the list of roads. So these are major roads. Now this also, as this stands now here, it's not going to be in the SF format, but luckily for us, this OSM data package has this function, which is called OSM data underscore SF, which is actually gonna coerce this into an SF format. Okay, and the very last two steps is, first of all, to make sure that we got the roads only for the bounding box that we asked for. And the second is to get this coordinates reference system of this one, which currently is WGS84 by default, into the one that is in tune with the noise raster data, which is actually 3035 or 3035. So they're not congruent at the moment, and now we're going to make sure that they become congruent. So let's go ahead and actually work with a new object here. Of course, we will pass this OSM roads into a pipe, and then what we need to first do is do some cropping here. So we can use the ST intersection and simply intersect with our region bounding box. But the region bounding box at the moment, it's not a polygon. So we first of all need to coerce it into a polygon, of course, within this ST intersection. So we can just write this function ST as SFC and then put the region bounding box here within this. All right, so this is gonna intersect. And once we intersect, we only need to make sure that, as I said, the coordinates reference system of the roads and the noise raster is the same. So we can use ST transform from the SF package. And then we want to transform here into the coordinates reference system. So we can use ST underscore CRS and then simply say here that we would like this to actually correspond to this noise raster clean object. So we have the noise raster, we have the OpenStreetMap roads for, of course, the extent of Brussels, and now we can go ahead and create the first very simple map. Let's start off by defining the colors. As always, I like to use HCL colors from base R. Here I specify that I have 5 values. I have 5 values because they go from 1 to 5, if you remember, and then 15 we turned it into a missing value. Then the second one is the palettes, and for this one I will use plasma palettes, which actually goes from yellow, signifying the lowest value, to blue, which is the highest value. Or actually, this is how it should be. Currently it's reverse. So what I want to put here is that I would like to put it in the order that I just described. Now that we have colors, we can take ggplot2 and start coding and prepare a code that will generate this map. So the first thing that we will want to add is that noise raster file. Remember, we didn't really coerce it into a data frame, so we need to use tidyterra here, which allows us to plot raster files without first converting them into a data frame within this ggplot2 environment. So we need to use here this geom_spat raster, and then here specify that our data is noise raster clean. But that's not all. We also need to coerce this into a factor so that our values are seen by ggplot2 as categorical and not continuous values. All right, now that we added this, we just need to add the major roads. So the data, of course, is the OSM major roads. And then for the color, we can choose, anything between black and grayish or white. I'm gonna opt here for a bit lighter gray color because remember, the higher the values, the darker the color of the noise will be. Of course, you can totally change this whatever you see fit. And then you can also change here the size, so the thickness of your lines. So we can, for example, go for, 0.5. We can make them a bit thicker, for example. And then finally here, what you can do is you can specify, of course, the colors that you previously defined using scale fill manual. You can, of course, omit here the type legend, or you can put simply, noise levels. Then for the colors, which is handled by the values attribute, we simply say that we're going to use colors here. And then for the NA value, which is actually still there, if you remember, we can just put here that we want to use, for example, the white color. And then within guides, we can also then specify, for example, how this legend is going to look like, which I'm not going to do at the moment. I'm just going to use here theme void to get rid of any extra extra elements around this plot itself. And then actually, once you run this entire code, you should be able to see the map of traffic noise for the major roads and the major roads themselves for the region of Brussels. Once you plotted this last map, you probably noticed also that it's a bit blurry when it comes to this combination of the noise raster and the roads. So it's not really clear what are the roads that are the noisiest there. So in a sense, we have some noise on our current map. What we're going to do in the next step is actually calculate what is the actual noise for each road, and then just simply plot the roads and color them by the level of noise they have. But in order to do that, we need to actually take several steps. One of them is to calculate this noisiness level for each road. Now, of course, this means that we need to intersect somehow that raster file, that noise raster file, with our roads SF file. And here is the major problem. The first problem is if you just do that, you're not going to get any values, or they're just going to be wrong values. What we can actually do here is we can thicken a bit our roads, and you can thicken the roads by creating small buffers around them. Let me show you how this looks like. So let's create something which can be called major roads buffer, and then let's use st buffer from the SF package. And then let's of course use OSM major roads here as the main object. And then we also need to specify the distance. Now the distance here can be specified in specific units that you want. And we can also set units here. So let's, for example, create a buffer of 50 meters around each of the roads. So this is gonna thicken a bit, as I said, make them fatter a bit. The thing here is, and what I noticed when I was actually running this analysis, that the more the bigger you buffer select here, the more imprecise it's going to be. So you need to find somehow like a proper middle ground here. So that would be probably somewhere between 20 and 50 meters if you add the buffer. Now, why are we actually adding this buffer here? We're adding this buffer because in the next step is we want to calculate, we want to extract maximum values, maximum noise values for these buffers. If this stayed only on the line level, a lot of values would have been missed and a lot of roads would not have these. So actually, let's go ahead and calculate now. Let's extract the values for each road that is now buffered. And over here, we're going to use another package that I didn't mention at the very beginning, but I will add it in the end to the script in the GitHub repo. And that is exact extract R, which is going to help us do that in no time. Terra also has the exact extracts function, which extracts values from a raster file based on some overlay, but it's actually quite slower. So let's create this new one. I'm going to call it, for example, major noise. And then, for example, here we can call it extract. And then let's use exact extract R and then exact extract function. So here you need to provide 3 arguments. X argument is the raster file that you want to use, from which you want to extract the values. So in our case, that's called noise raster clean. Y argument is the overlay for which you want to calculate, so for which you want to extract the values. In our case, that's the major roads buffer. Remember buffer because we thickened it. And then the last one is called fun, which is not a fun, but a function. And here you need to specify what kind of a function you want to get here. All right. So here you can, for example, take a maximum, minimum, or you can take also the majority. The majority or mode is the one that is also pretty cool because it just gives you the majority one. Because our values are categorical, it makes sense to take, for example, minimum, maximum, or this mode or categorical. So the resulting output of this is a data frame, which is going to have the same number of rows as our roads data. So what we can do is simply we can do column-wise merger of these two. And this is what I'm going to do next. This is essentially going to create a new SF object that we will then use afterwards for, of course, plotting. And this object I will call major roads noise SF. So as I said, column-wise binding, which is called here C binding R. And then I need to specify first of all, the name of the roads. So that's OSM major roads. So remember here, we're not using buffer anymore. The buffer, the roads, we only use for the calculation. Now we're going back to the OSM roads, which are of the normal size. And then the second argument is this newly created data frame that has the extracted value for each of the roads. All right, guys, we're almost ready to create our final map. But before we do that, I simply wanted to here show you this final object that we created of roads with noise level. And you can see here that it has a bunch of almost 300 columns. This is because the OpenStreetMap object, the original one which we loaded, it has all these field names. But don't worry, we only need this one, 284, which has this weird name, but it basically just simply inherited name from the data frame that we merged column-wise with the SF object. So we simply need to copy this one and then use it in the ggplot2 code. Before we write the ggplot2 code, I want to also get the street view layer so that you can put all these maps and their noise level into a geographic context. And fetching these street view layers is quite easy because we can use map tiles, and map tiles has a function which is called get tiles, which allows you to do that. Now, this works in a sense that you need to pass here a bounding box, so region B box in our case, and then you need to choose the provider from which you're going to be taking this. So what I like to use is CartoDB Positron, which offers a bit of a grayish background. If you're interested in other options, you can also check the Map Tiles project website. The third attribute is zoom. So this is the level of detail where it goes from 1, which is basically zoomed out, to I think 14 or 15, which is completely zoomed in. Now this of course really depends on the size of your region. For me, for example, in this case 12 works. When I say works, it means that it returns in a fairly fast way the street view layer, but it also means that the labels of the streets are gonna be also crisp. Now if I increase this, then the problem is that the level of detail is of course better, but the labels are very, very blurry and it doesn't look good. All right, the fourth one is that you want to only crop for the area that you need. And the final one is that you don't want to reproject into the native coordinates reference system. All right, now that we have the street view layer, which you can also run, is to create, of course, our final map and put together all these layers that we have. I'm going to start off by calling force ggplots function. The second thing is I want to add this street view layer, and again I can use tidyterra because it allows me to work with raster files without coursing them into data frame. But this time we're going to be using gmspatraster RGB because we have an image with RGB values, and that image is called streets. So we're going to just be passing it here. And then the second layer we need to add is an SF object, and that's why I'm using here GMSF. But this time what I would like to do is I would like to subset this object, which is called major roads noise SF. I want to subset and I want to actually remove all the missing values. And this is the way to actually remove them. Now, the only thing I actually want to do here is check again. What are the names? Okay, so the name here is major noise extract. So that's the name, this 284. That's the name of this field. So this is going to remove any missing values, of course. And then once we define this, we also need to define our main aesthetics. And that's, of course, if you're working with lines like we are, that's called color. So for the color, we're going to be using, again, this one, but we're also going to be coursing it into a factor because these are essentially categorical values going from 1 to 5 or from 0 to 5, of course, depending on your data. And then outside the aesthetics, you can also choose a constant. For example, the thickness of your road lines, and I'm going to go for a bit thinner lines this time, 0.25. Okay, now that you added all the layers here, you can go ahead with the customization. And one of the things that you want to definitely customize here is the color. Because we're using categorical values, you need to use here scale color manual. And then I will omit here the legend title. Of course, we're talking about noise levels. If you want, you can also include it. And the second one is the colors that we're going to use. So this is called values. I'm going to pass here the colors string that we already have. And then if there are any NA values, if there are any NA values left, I just want them to be in white color. We can also customize the legend here using the guides argument, but be careful to choose here the one that corresponds to your main aesthetic, which is the color. And then here within guide legend, you can specify so many things from the width to the height of your legend key. But what I like to do here is, because the legend key is essentially a line, I would like to create a bit thicker lines in the legend. And for that purpose, you can use this override AES, which is going to override the main aesthetics. And here I can choose a bit thicker lines, for example, size equals 3, so that we can clearly see what are the colors associated with each legend value. And once you do that, you can simply here choose theme void to get rid of any excess elements around your plot. Once you run this, you will be finally able to see the map of noise levels for each major roads in Brussels, colored from light colors for yellow, which is the lowest noisiness level or 1, to the darkest navy blue color, which is the highest level or 5. And you can clearly see here on this map that actually the highest values are clearly associated with motorways. And that's all for today, folks. In today's tutorial, you learned how to extract traffic noise levels for different major roads and then to create a very effective map. So we created one such map for the Brussels region, but I'm really looking forward to your own projects and how you take this tutorial on a journey across the globe and create some awesome regional or country maps of your interest. If you're interested in replicating today's analysis, I prepared the link to the GitHub repo in the description box below, so do check it out. Feel free to clone it, reuse it, modify it as you see fit. If you have any questions, comments, or just general feedback, feel free to reach out to me here on YouTube, but also on Instagram and X. If you're new to R and you seek to expand your data visualization and geospatial knowledge in R, I prepared a few cool tutorials for you, so do check them out. See you next time.